Okay, so lab 5 is the MOSFET differential pair with active load. We've already done the hand calculations. Now we need to do the simulations for it. I scroll down to here. We need to first verify the Q point voltages, the DC operating point, while the gates are grounded. So let me open up my project because I've already gotten everything put together already. So we got plus or minus 5 volt supply. I have NMOS and PMOS model parameters on the bottom here. I'll get some simulation warning about the version NCH parameters, but that's okay. You can just ignore those. And RF is 1.8K still from lab 4. That's what gave us 4 milliamps bias current. And NMOS and PMOS should all have widths of 1,000 and lengths of 10 micron. Every single transistor needs those parameters. And just wire up the circuit as shown and you should be good to go. Now I have VCM set to 0 here, which is just going to put 0 volts on the gates of both of these transistors for the DC operating point. So I'm just going to delete these operating conditions here. And if I go to run a simulation, I'm just going to do DC operating point, very last tab up top, run the sim, and it will tell you all the terminal voltages of all the transistors, all your node voltages, as long as you name them. Something nice in the schematic, you can easily point those out here. And all your currents as well. So for example, RF, if I look for I parentheses RF, which is right here, it says the current is 4.1756 milliamps, which is close to 4 milliamps is what we were hoping for. So that makes sense. If I look at, we already know VG1 and VG2 should be 0. So if I double check those, VG2 is 0, VG1 also 0. And we just need to measure VTail. VTail is minus 2.75 volts, which means VGS of the input pair is 2.75 volts. And that's our Q point. You could also look at the drain current of M6, which is right here. That's pretty close to what our reference current was, 4.15697 milliamps. I'm just going to close out of that. It's going to be upset about some of the modeling parameters, like I said. You can just ignore it. So the next part of the lab assignment is to put a differential signal of 40 to 60 millivolts peak to peak at a frequency of 1 kilohertz. And we need to measure the peak to peak input signal and output signal and make sure we got the differential gain that we're supposed to. So I've set this up to be 1 millivolt peak right now. So let's change that to be 40, I think is what it says. Accidentally skipped ahead. 40 millivolts peak to peak. So that corresponds to 20 millivolts amplitude at 1 kilohertz. 1 kilohertz. Okay. VCM can still be 0 here. If you did the Prelab correctly, you'll get a result that says VCM min is around minus 0.4 volts. So as long as we stay above that, we'll be okay. We'll find out when we do the common mode input signal that we have to adjust this because the common mode input has to be very high. But we'll get to that in a second. So 20 millivolts amplitude is 40 millivolts peak to peak. Let's run a transient sim here. The period is 1 millisecond, so let's run for 3 milliseconds and a set time of, I don't know, 1 microsecond. Should be good. Click OK. It'll run the sim. You can just ignore those warnings. And I'm going to delete some old points I have on here. Okay. So right now it's plotting VG2, which isn't really interesting. So let's plot VG1. You can see a little waveform there. If we want to move it to a separate plot, we can do add plot plane and just drag it up there. So here's our input signal. You can see it's 40 millivolts peak to peak. And we want to measure the output. So let's put some cursors on here at the min. Draw cursor position and one at the peak. Cursor position. And if you take the peak to peak difference, 2.89 minus 1.87, that will tell you the output swing. Divide that by the input, which was 40 millivolts peak to peak, and that will give you your differential gain. And you want to do this for 3 different values of input signal. So maybe 40, 50, and 60 millivolts peak to peak. So for pictures, you want a picture of the schematic. You want a picture of this waveform showing input and output like I showed. You want to measure VGS, which I've already done. I've shown that. For this table, you want to measure the differential output swing, which is here. I just measured one of those points. You can calculate the voltage gain by dividing output by input, and you can convert that to dB by 20 log of this number. And the last part of this is to do the common mode gain. So if we go back to the schematic here, and we slightly modify things, and instead apply the input signal to both sides, like so. I'll delete that net name, otherwise it'll probably complain that there's 2 names for this net, VG1 and VG2. So let's get rid of that potential error. And now we have a common mode signal to both sides of the amplifier. And it says to use 1 to 3 volts peak to peak. So we're going to modify the sine wave to be 500 millivolts amplitude. 500 millivolts amplitude, which is 1 volt peak to peak. And actually, you know, I'm going to try the 1.5 volts just to show a potential problem. So 1.5 volts amplitude is 3 volts peak to peak, which is the last point you probably do. And we'll do it with 0 volts common mode input first and see how it works. And frequency can still be 1 kilohertz, so nothing else needs to change. Let's just run the sim. If you do that, you'll see you have your 3 volts input, but you'll also see that the output isn't really behaving like a sine wave anymore. And this isn't going to give you good results. And the problem here is when the input signal is swinging low, it's actually starting to turn off the M6 transistor. So what we want to do here is adjust the common mode voltage, and we can just try 1.5 volts and see if that's sufficient. It should be. So let's rerun the simulation and see if it looks better. And there you go. Now you have a nice looking sine wave at the output. So we've moved up the input signal so that it doesn't swing minus 1.5 volts to 1.5 volts. It swings 0 to 3 volts now. And the problem was when the input was swinging below around 0.5 that it started to turn off M6. But we made it so that it never swings that low anymore. So the output is always a nice sine wave now. So again, we want to measure peak to peak of the output. So draw cursor position. Cursor position. And if you take the peak to peak there, it looks like about 40 millivolts, 41 millivolts. So for a peak to peak input of 3, the output is around 0.04. You can give a better measurement than that and just averaging, and just ballparking the number. So the gain is equal to the output divided by the input. So it should be a small value. And you can take 20 log of that to get the gain in dB. But we expect the gain to be small. Ideally, the output signal doesn't respond at all to a common mode input. And this note is just telling you about, for a large common mode input signal, you might have to add some common mode offset, like we just did. So once you have these tables filled out, you can do the average differential gain. You can just average this column if you'd like. And average common mode gain, just take the average of those three. And you can compute the common mode rejection ratio by taking the ratio of those two numbers. And that is all. So once you've gotten all these pictures, all the data, just make sure you submit it along with your LT Spice files to my courses.